Hi, and welcome to a friendly introduction to Bayes' theorem and hidden Markov models. My name is Luis Serrano, and I work at Udacity. I teach machine learning and artificial intelligence courses there. So, let's start with the following scenario. We have two friends, and their names are Alice and Bob. And they live very far apart, and they talk on the phone. So, Bob has a mood that changes based on the weather. So, if it's sunny, then Bob is happy. And now he tells Alice on the phone that he's happy, and so she infers from that information that it must be sunny. And if it's rainy, then Bob gets grumpy, and so he tells Alice on the phone that he's grumpy, and from there she infers that it must be rainy. So, small summary, the weather can be rainy or it can be sunny, and if it's sunny, then Bob is happy, and if it's rainy, then Bob is grumpy. And so he tells Alice his mood, and she guesses immediately what the weather is based on his mood. So far so good. Let's make the problem a little more complicated. Let's say that Bob is mostly happy when the weather is sunny, but there are some exceptions, and Bob is mostly grumpy when the weather is rainy, but there are also some exceptions because due to other circumstances. So let's say that we've calculated some probabilities, and we have concluded that when it's sunny, then Bob is happy with a probability of 80%, so 0.8. And when it's sunny, then Bob is grumpy with a probability of 20%, so there's 0.2. And likewise, if the weather is rainy, then Bob is grumpy with a probability of 60% and happy with a probability of 40%. So now we're back to our scenario, and the type of questions that we're gonna look at in this video are the following. Let's say Bob says, oh, this week I was happy, then the next day I was grumpy, and then the next day I was happy, and then Alice has to come up with a guesses that says, oh, maybe it was sunny one day, then rainy, and then sunny, or something along those lines. So let's say that one day they talk, and Bob says, well, this week was an emotional roller coaster. On Monday I was happy, but then on Tuesday I was pretty grumpy. On Wednesday I was happy again, but then on Thursday I was grumpy, and then on Friday I was happy, and then on Saturday I was grumpy. So what can Alice infer? Well, based on what she knows, she can only say, well, since sunny makes Bob happy, then probably Sunday was sunny, and since rainy makes Bob grumpy, then probably Tuesday was rainy, and same reason, probably Wednesday was sunny, then Thursday was rainy, then Friday was sunny, and then Saturday was rainy. Now the question is this a likely scenario? It is based on Bob's mood, but it's kind of strange to have sunny, rainy, sunny, rainy, sunny, rainy. Like, weather does not behave like that. It depends on where you live. But the idea is that if a day is sunny, then it's kind of likely that the next day will be sunny too. And if a day is rainy, maybe it's likely that the next day is rainy. So maybe it's this sequence that gives us a problem. Maybe we need to figure out how likely it is that this sequence happens. So we go back to our model. We have sunny and rainy, and the probabilities of each one of them making Bob happy and grumpy. And let's actually start looking at the probabilities of a day giving us the next day's weather. So if today is sunny, let's say that the probability of tomorrow being sunny is going to be 80%. And since the remaining is 20%, then the probability that today is sunny, that tomorrow is rainy, is going to be 20%. And likewise, let's say that if today is rainy, then tomorrow is going to be rainy with a probability of 60% and sunny with a probability of 40%. They have to add to 1, right? And so what we have is now a hidden Markov model. So a hidden Markov model has two types of states. It has some observations, which is what we see. So Alice can only see Bob's mood. She doesn't get to see the weather. So those are observations. And then the weather is called the hidden states because Alice doesn't get to see the weather. She can only infer it from the observations, which is Bob's mood. And these numbers are called transition probabilities because it's the probability of going from one hidden state to another. And these ones are called the emission probabilities, so the probability that the observations are emitted from the hidden states. If you like letters instead of symbols, then think of this as your hidden Markov model. So in this video, we're going to answer 4 questions. The first one is, well, how do we find these probabilities? They look a little magical, these 80% and 60%, but we can infer them from data. The second question is, what is the probability that a random day is sunny or rainy, independent of Bob's mood? The third one is, if Bob is happy today, what's the probability that it's sunny or rainy? So now the weather depends on Bob's mood. And the fourth one is, well, if these type of questions is, if for 3 days in a row Bob is, say, happy, grumpy, happy, then what was the weather most likely to be? So let's start with the first question. How do we find these probabilities? So as we said, they look a little magical, but actually it's not that hard to infer them. Let's say we have some data that we've looked at and that we've been able to study the past weathers. So we see that the weather is sunny, 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 rainy, rainy, etc. And all we're going to do to infer this probability is we're going to see how many times a sunny day is followed by a sunny day. So how many times does sunny and then sunny appear in the sequence? Well, we can see that the first 2, then the second 2, then the third 2, etc. So this appears 8 times. And how many times does sunny and then rainy appear? It only appears twice, in the 4th position and then further. So therefore, the probabilities are these numbers normalized, right? So if today is sunny, then tomorrow is going to be sunny with 80% probability and rainy with 20% probability. And now let's do the same thing for rain. So how many times does a rainy day is followed by a sunny day? Only twice. And how many times is a rainy day followed by a rainy day? 3 times. So these 2, 3 are a 40-60 split. So it's 40% likely that tomorrow is sunny if today is rainy, and 60% likely that today is rainy, that tomorrow is rainy, given that today is rainy. So that's how we calculate our transition probabilities. So now let's calculate the emission probabilities, and it's equally easy. We now just have to look at previous data. So we look at all these observations, and we see, okay, how many times has a sunny day made Bob happy, and how many times has a sunny day made Bob grumpy? Well, 8 times it made it happy, as you can see, and 2 times made him grumpy. So therefore, this is an 80-20 split. So our probabilities are 80% and 20%. And now how many times does a rainy day make Bob happy, and how many times does a rainy day make Bob grumpy? And we can count them. It's 2 and 3. So this is a 40-60 split. Therefore, this is how we calculate our emission probabilities. So question 1 has been answered. Obviously, these are just estimations of the probabilities, but if we have long enough chains, we can get a pretty good estimations of what the actual probability is. So question 2, what is the probability that a random day is sunny or rainy? So independent of Bob's input, let's just say one day Bob didn't want to talk to us, so he didn't say anything. So now Alice has to figure out, well, she can't really figure out what weather it is, but what are the probabilities, right? How likely is it that it's sunny, and how likely is it that it's rainy? So I'm going to first give you like the super easy kind of cheating answer. The answer is, if we have a lot of data, we have days, we can just count how many days are sunny and how many days are rainy. And in here, 10 days are sunny, 5 days are rainy. So we have a 2/3, 1/3 split. And those are our probabilities, 67% and 33%. So as I said, that looks a little bit like cheating. So let's actually find them from the transition probabilities. So let's think the following. If today is sunny, it could have been because yesterday was sunny or because yesterday was rainy. So yesterday was sunny, gave us today sunny with probability of 0.8, and rainy gave us sunny with probability of 0.4. So we have the following equation. Probability of sunny is 0.8 probability of sunny plus 0.4 probability of rainy. And likewise on this side, if it was rainy today, it's because yesterday was either sunny or rainy. And from the sunny, we get 0.2 times sunny. And from the rainy, we get 0.6 times rainy. So now we have a system of two equations and two variables that we have to solve. Except not really, because if you look at them carefully, these two equations are the same equation disguised. So we need another equation. But the other equation comes easy, because every day it's either sunny or rainy. So these probabilities must add to 1. And therefore, if we solve this system of equations, now we get 2/3 and 1/3. So we conclude that the probabilities are 2/3 for sunny and 1/3 for rainy. So if Bob gave us no information, then Alice knows that, well, it's 2/3 likely to be sunny and 1/3 likely to be rainy. So that is the second question answered. Let's answer the third one. If Bob is happy today, what is the probability that it is sunny or rainy? So basically, we start at square one, which says Bob gave us no information. And Alice knows that it's 2/3 likely to be sunny and 1/3 likely to be rainy. But all of a sudden, Bob says, no, actually, no, I'm happy. So if he's happy, it means it's more likely for it to be sunny. So all of a sudden, in Alice's head, the probabilities change. They may change to this or they may change to something else. But the idea is that they increase, the probability of being sunny increases. Now, if Bob says, no, actually, no, I'm grumpy, that means it's more likely that it's rainy. How much more likely? We'll see. Let's calculate these probabilities. So this is actually called Bayes' theorem, and it's one of the most important theorems in probability and in machine learning. It's really about inversion of events, right? Because you have the event of being sunny or rainy, and that changes Bob's mood. But all of a sudden, we're supposed to infer from Bob's mood the weather, if it's sunny or rainy. So we're switching the events, and that's Bayes' theorem, and it's really fundamental in probability and machine learning. So let's say today is Wednesday, and Bob is feeling happy. So there are two possibilities, that it's sunny or that it's rainy. And let's recall the probabilities that we have in our hidden Markov model. But we're only caring about one day, right? So we don't really need to worry about the transition probabilities. All we need to care is today was sunny with a probability 2/3 and rainy with a probability 1/3. Those are we may call the prior probabilities. So the initial probabilities before we know what is Bob's mood. And now let's derive Bayes' theorem. So pay close attention to what's happening here. We know from the prior probabilities that it's 2/3 likely to be sunny and 1/3 likely to be rainy. So on an average scenario, we would have 2 sunny days and 1 rainy day. Now let's look at the first sun on the left. So that sunny day made Bob happy with an 80% probability, and it made him sad with a 20% probability. So if there were 5 days that were all sunny, then Bob is happy on 4 of them and grumpy on 1 of them. And let's do the same thing for the second sun. So if we have 5 sunny days, Bob is happy on 4 of them and grumpy on 1 of them. And now let's look at the rainy one. So rainy weather makes Bob happy with a probability of 0.4 and grumpy with a probability of 2.6. So if we had 5 rainy days, Bob is happy 2 of them and grumpy on 3 of them. So here we have 15 days, right? And now let's look at how many of these days is Bob happy. Well, Bob is happy all these days, and he's grumpy all these days. Okay, now this is where the magic happens. We now know that Bob is happy today, and we want to figure out if it's sunny or if it's rainy. So if Bob is happy today, he tells us, today I'm happy. So therefore, now we have 10 days because we don't care about the sad days. And among these 10 days, what is the probability that is sunny? Well, 8 of these 10 days are sunny and the other 2 are rainy. These are the 8 that are sunny. So therefore the probability that is sunny is 8 divided by 10. And now the probability that is rainy, given that Bob is sad, well, these are the 2 rainy days and the other 8 are sunny. So therefore it's 2 over 10. And those are called the posterior probabilities. So now that we know that Bob is happy, these are the probabilities that it's sunny or that it's rainy. Notice that it's higher probability to be sunny because we know Bob is happy, and since sun makes him happy, it's more likely that it's sunny. And now let's do the same thing with the sad days. So we had 5 sad days, and 2 of them were sunny and 3 of them were rainy. So if Bob tells us that he's sad, then the probability of sunny given sad, well, these are the 2 days that are sunny out of 5. So the probability that sunny given that Bob is sad is 2 out of 5. And the probability that is rainy given that Bob is sad, well, it's these 3 days divided by the total, so 3 out of 5. And that is exactly Bayes' theorem. So these are the posterior probabilities. So let's recall. The prior probabilities are 2/3 and 1/3. This is the probability that is sunny or rainy given no information. Once we know that he's happy or we know that he's sad, then we have new probabilities, and those are called the posterior. Okay, but now we've answered the first 3 questions, and let's answer the 4th one, which is the super interesting one. And the question is going to be along the following lines. If I have a sequence of days and I know the mood of Bob, then what can I guess about the weather? So for example, if for 3 days Bob tells us he's happy, grumpy, and happy, then what was the weather? So let's say he says, I was happy, I was grumpy, and I was happy for 3 consecutive days. And then Alice is supposed to guess, oh, maybe it was rainy, then sunny, then rainy, and then sunny. Maybe that's not the answer, but she's supposed to pick sort of the most likely scenario. So let's look at a simpler case. Let's say we have 2 days, Wednesday and Thursday, and on Wednesday, Bob was happy, and on Thursday, Bob was grumpy. So how many possible scenarios we have for the weather? Well, on Wednesday, it can be sunny or rainy, and on Thursday, it can be sunny or rainy. So we have to study 4 scenarios. For Wednesday and Thursday, we have sunny, 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 rainy, rainy, sunny, and rainy, rainy. And what we're going to do is we're going to take each one of them and calculate what is the probability that given these weathers, Bob was happy and then grumpy, and then we're going to pick whatever gave us the highest. That's called maximum likelihood estimation. So let's pick one of them. Let's pick this one and calculate the probability. So we know that on Wednesday it was sunny, on Thursday it was rainy, and on Wednesday Bob was happy, and on Thursday he was sad. So let's calculate the entire probability of all this happening at the same time. Let's start with what is the probability that Wednesday was sunny? Well, we know from the prior probabilities that it's 2/3 or 0.67. Now, if Wednesday was sunny, what's the probability of Bob being happy? Well, we know that's 0.8 because that's the probability that a sunny day makes Bob happy. Now, given that Wednesday was sunny, what's the probability that Thursday was rainy? We'll know that transition probability is 0.2. And now, given that Thursday was rainy, what's the probability that that made Bob grumpy? We know that that is 0.6 because it's the emission probability. And now, by the laws of conditional probabilities, this may be something you want to check on a sheet of paper, but the probability of the whole thing happening is the product of all these, which ends up being 0.064. So if you want to work it out by yourself, that's a good exercise. But these are the 4 scenarios, and the probabilities of these 4 scenarios are 0.085 for sunny, sunny, the one we already calculated, 0.064 for sunny, rainy, 0.0107 for rainy, sunny, and 0.048 for rainy, rainy. So we look at all of these, and the one that gives sunny, rainy with a higher probability is actually this one. So we're gonna pick the one that made happy, grumpy, the most likely to happen. So that is called maximum likelihood. We pick the model that makes our observations the most likely to happen. And so that's it. That means that if Bob says happy, grumpy, then Alice says it was probably sunny and sunny. Now what happens if there's 3 days in a row? So if Bob says on Wednesday I was happy, on Thursday I was grumpy, and on Friday I was happy. So again, 2 possibilities for the weather each of the days. Therefore, we have to look at 8 possible scenarios. Sunny, 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 rainy, etc. all the way to rainy, rainy, rainy. It's getting a little out of hand, but we can still do it. Let's look at this one. So let me do it very quickly, since we've done it. The probability of this whole scenario happening. For it to be sunny the first day is 2/3. For that to make Bob happy is 0.8. For that to make Thursday rainy, given that it's Wednesday sunny, is 20% or 0.2. For the Thursday rain to make Bob grumpy is 60%. For the Thursday rain to create sun on Friday, 0.4, 40%. And for the sunny Friday to make Bob happy, that's 0.8. We multiply these and we get 0.02048. Now all we have to do is check this for 8 cases, and I won't do it here, but actually you can check, and this is the better one. So that gives us the answer. Things are getting complicated, right? If we have 4 days, happy, grumpy, happy, happy, then now we have to check 16 cases. So in general, you have to check 2 to the n, and that just grows too fast. It grows exponentially, and that's not what we want. So we want to do something more intelligent than having to check 2 to the n things each time. And this is what we're going to do. We're going to check a lot fewer cases. So let's recall that this is our hidden Markov model with our transition probabilities and our emission probabilities. And let's go to a big case. Let's say that Bob said, okay, in the last 6 days, I was happy, happy, grumpy, 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 and happy. And we're going to find some chain that gave us in the highest probability. It's probably not this one. So what we're going to teach now is the Viterbi algorithm. The Viterbi algorithm, if you know dynamic programming, that's exactly what we're going to do. So instead of checking 2 to the n things, we're going to start checking a few things and storing the maximum of what we've checked so far, and then comparing things. And at the end of the day, we're going to have to check much less than 2 to the n paths. So let's look at this scenario, okay? And let's focus on Saturday. What happens on Saturday, the last day? Well, it could be sunny or it could be rainy. What if it's sunny? Let's check if it's sunny, because what we're going to do is compare what gave us a better probability, if it was sunny or if it was rainy. So if it was sunny, then let's say that a bunch of paths led to this being sunny. These are many possibilities. At the end of the day, we really only care about the one that came with the maximum probability, right? So that's what we're going to do at every stage. We're going to record the best path up to here, and that probability multiplied by the probability that our sunny day made Bob happy is what we're going to compare with the best path up to here times the probability that that rainy day made Bob happy. Okay, so far we only have to record the best path up to here for the sunny day and the best path up to here for the rainy day. Now let's look at the top one, the best path up to the sunny day. So the previous day could have been sunny or it could have been rainy, right? And so we just need to know the best path up to here that ends in sunny times the probability of that making Bob grumpy, and compare it with the best path up to here that ended up in a rainy day, and multiplied by the probability that that made Bob sad. So basically at any stage we just have to compare 2 things. And if that was a little confusing, that's okay. This algorithm is a little confusing, but once you see it, it'll it'll be very simple. Let's go from the other direction. So let's start calculating the best path up to each point. So for Monday, we know we have two scenarios, that it's sunny or that it's rainy, and the probabilities are 0.67 or 2/3 for sunny and 0.33 or 1/3 for rainy. And now let's calculate the probability that each one of them gave us the observation we have so far. So the probability that it's sunny and that made Bob happy on Monday, it's 0.67 times 0.8, because 0.8 is the probability that Bob was happy. And that gives us 0.533. That's our probability so far if the first day is sunny. And now for the rainy one, we say, okay, the probability that it was rainy and that made Bob happy was 0.33 for it being rainy times 0.4, which is the probability that the rain made Bob happy. So that's 0.33 times 0.4, which is 0.133. And now these are the winning numbers up to here. Now let's look at the next day. It can be sunny or it can be rainy. So if it's sunny, what happens? Well, we have to choose between two things, that yesterday was sunny or that yesterday was rainy. Let's see what happens when yesterday was sunny. So if Monday was sunny and Tuesday was sunny, then the probability of the transition is 0.8, and the probability of the emission of Bob being happy is also 0.8. So our probability so far is what was before, which is 0.533 times 0.8 times 0.8, and that is if Monday was sunny. Now if Monday was rainy, then we have 0.133, which is the probability of so far of Monday being rainy, times the transition probability, 0.4, times the emission probability of the sun making Bob happy, which is 0.8. So we have to decide between these two. And the one that is the highest is the one that we're going to pick, because we don't care about the other one. We're trying to maximize the probability, so we may as well maximize it at this point. And that is really the trick of the Viterbi algorithm. That's really because we're going to only record the bigger one. And the bigger one here is actually the first one that gives us 0.341. So let's record a 3.1 there too. And now let's look at what happens when it is rainy. If Tuesday was rainy. So if Tuesday was rainy, now two numbers are competing. The number coming from if it's rainy, so if it's sunny, which is 0.533 times 0.2 times 0.4, the previous probability times the transition times the emission, and the number in the bottom, which is if Monday was rainy, then it's 0.133 times 0.6 the transition probability times 0.4 the emission probability. So these two numbers compete, and the larger one, which is the first one, gives us 0.043. Now we can keep going, and feel free to pause this video and actually do them yourself. But basically the algorithm goes like this. We're always picking the larger one between the two competing numbers. Actually, I wrote a little program, and I'll put it on the comments that calculates this. So this is the entire algorithm, where I'm always recording the higher probability path up to there. And then we have these numbers. So at every point, what is recorded is the largest probability of the choice of weathers up to that point that end in that point. And now all we have to do is just pick the largest one each day and walk along that path. So we know that the higher probabilities are sunny, 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 rainy, rainy, sunny, and that's going to be our answer. So in the end, if Bob says my moods are happy, happy, grumpy, 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 happy, then Alice thinks to herself, well, most likely the weathers were sunny, 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 rainy, rainy, and then sunny. So as I said, if you're curious about how to calculate this one fast, I wrote a little program that codes this Viterbi algorithm. However, if you have bigger data or something, I recommend some packages in Python. One is called Pomegranate and the other one is called HMM Learn. So I'm going to leave you with a question. How did Alice figure this out? It seems like we used a little too much data. So for example, we had all these emission probabilities and all these transition probabilities, but it could just be that the hidden states are so hidden that we don't even know the transition probabilities. When this is the case, then I recommend you to read on the Baum-Welch algorithm, or maybe in the future I can make a video about that. It's very interesting. And I'm going to leave you with some applications. So the first application of HMMs is part of speech tagging. So if I give you a sentence and you want to tell which word is a preposition, a verb, a noun, etc., that is done with HMMs, where the observations are the words in the sentence and the hidden states are the tags. Also for robot localization, it's used a lot. In this case, it's an HMM where the observations are what the robot sees. So how far it is from walls, or like what the radars tell it. And the hidden states are basically the coordinates of where the robot is actually located. You're supposed to find where is it most likely that the robot is located based on the observations. Another place where HMMs are used very widely is genetics, because genetics involves a study of very complex sequences of DNA, and as we can see, HMMs are very widely used for sequences. And another place where they're very much used is speech recognition, because in speech recognition you would have the observations, which are the signals that you hear on the sound, and the hidden states, which are the words that you're supposed to guess that the person is saying. So that's all, folks. Thank you very much for your attention. I really enjoyed making this video, and if you enjoyed it too, please hit subscribe, hit like, or share it in social media, share it with your friends. And I love it when you comment. I really enjoy reading people's comments and what you learned or what suggestions you have. In particular, if you have suggestions of topics, somebody suggested this HMM video, and that's why I did it. So let me know what topics you'd like to cover, and I'll try my best to make a video about it. And yeah, these are my coordinates. I got a blog on GitHub, and my Twitter is Louis Likes Math, so feel free to shoot me a tweet. And if you really like what you saw, I teach a lot of these courses in much more detail at Udacity. I teach artificial intelligence, deep learning, machine learning, etc. So if you like it, take a look at our webpage. There's a lot of interesting courses. Many of them you can take for free. And if you want to be more serious, you can enroll in a nano degree program. So thank you very much, and see you in the next video.